Welcome to Askprep, your trusted companion for NEET and JEE preparation. Today we will study about a very important topic of chemistry, which is periodic table and periodicity, trends in atomic and ionic radius. The periodic table is one of the most powerful tools in chemistry, serving as a map that organizes elements based on their properties and atomic structure. Understanding periodicity, or the recurring trends in element properties, helps us predict chemical behavior, reactivity, and atomic interactions. One of the most fundamental trends observed in the periodic table is the variation in atomic and ionic radii across periods and down groups. Atomic radius refers to the size of an atom, which is determined by the distance between the nucleus and the outermost electrons. However, since atoms do not have sharply defined boundaries, the atomic radius is often estimated based on different methods, such as covalent radius, metallic radius, and van der Waals radius. Regardless of the method used, the general trends in atomic size remain consistent across the periodic table. As we move across a period from left to right, the atomic radius decreases. This phenomenon occurs due to an increase in nuclear charge, or the number of protons in the nucleus. With each successive element in a period, an additional proton is added to the nucleus, and an electron is added to the same principal energy level. The increasing positive charge of the nucleus exerts a stronger electrostatic pull on the negatively charged electrons, drawing them closer to the center. As a result, the size of the atom contracts, despite the increase in the number of electrons. However, moving down a group leads to an increase in atomic radius. This trend occurs due to the addition of new electron shells, which are farther from the nucleus. Even though the nuclear charge also increases, the effect of additional energy levels outweighs the increased attraction from the nucleus. The outermost electrons experience shielding, where the inner electrons partially block the nuclear pull, reducing the effective nuclear charge felt by the valence electrons. This allows them to remain farther from the nucleus, resulting in a larger atomic size. When atoms lose or gain electrons, they form ions, which exhibit trends in ionic radii that differ from neutral atoms. Cations, or positively charged ions, are always smaller than their neutral counterparts. This is because losing electrons reduces electron-electron repulsion, allowing the remaining electrons to be drawn closer to the nucleus. Additionally, if an entire outer shell is removed, the decrease in energy levels leads to a drastic reduction in size. For example, sodium has a much larger atomic radius than its Na+ ion because the removal of one electron results in a stable, smaller configuration. On the other hand, anions, or negatively charged ions, are larger than their neutral atoms. When an atom gains electrons, the increased electron-electron repulsion pushes the outermost electrons farther apart, leading to an expansion in size. The nuclear charge remains the same, but the additional electrons increase repulsion forces, which prevents the nucleus from pulling the electron cloud as tightly as in a neutral atom. This is why chloride ions are significantly larger than neutral chlorine atoms. Ionic radii also follow periodic trends similar to atomic radii. Across a period, cations generally decrease in size due to increasing nuclear charge pulling the electrons closer. The trend continues with anions, which also show a decrease in size as nuclear charge increases across a period. Moving down a group, both cations and anions increase in size due to the addition of energy levels, similar to the trend observed in atomic radii. Understanding trends in atomic and ionic radii is crucial for explaining various chemical properties, such as bonding, reactivity, and intermolecular forces. Smaller atoms tend to have higher ionization energies and greater electronegativities because their electrons are held more tightly by the nucleus. Conversely, larger atoms have lower ionization energies and electronegativities, making it easier for them to lose electrons and participate in chemical reactions. Moving down a group in the periodic table, atomic radius increases. This is because as we move down, electrons are added to higher energy levels, which are farther away from the nucleus. Although the nuclear charge also increases, the effect of electron shielding plays a dominant role. Inner electrons shield the outermost electrons from the full effect of the nuclear charge, weakening the attraction between the nucleus and valence electrons. This allows the atomic size to expand. For example, lithium is much smaller in size compared to cesium, which is found lower in the same group. Another key trend is the comparison of ionic radii within an isoelectronic series, ions that have the same number of electrons but different nuclear charges. In such a series, the ion with the highest nuclear charge will have the smallest radius because the greater attraction pulls the electrons closer. For example, O superscript 2, F, Na, and Mg superscript 2 all have the same number of electrons, but their radii decrease as the nuclear charge increases from oxygen to magnesium. Periodic trends in atomic and ionic radii also play a role in biological and industrial processes. In biological systems, ions like sodium, potassium, and calcium are essential for nerve impulses, muscle contractions, and enzymatic reactions. The relative sizes of these ions influence their transport across cell membranes and their ability to interact with biomolecules. In materials science, understanding atomic sizes helps in designing semiconductors, catalysts, and other advanced materials with tailored properties. By analyzing the periodic table and understanding periodic trends, chemists can predict the behavior of elements in different environments. The relationships between atomic size, ionization energy, electronegativity, and other periodic properties allow us to rationalize chemical bonding, reactivity patterns, and molecular structures. Mastering these concepts is fundamental for students preparing for competitive exams like NEET and JEE, as they form the foundation for understanding more complex topics in chemistry and beyond. Thank you. This is Askprep, your guide to mastering NEET preparation. Let's decode complex topics and simplify your journey to success.